Something happened in China that forced the global auto industry to look closely at a machine most people would have ignored completely. It was not a futuristic sports car, a giant battery, or a dramatic prototype covered in glowing lights. It was a silver metal box, roughly the size of a suitcase, weighing about 75 kilograms and looking like an ordinary piece of industrial equipment. But inside that unremarkable box was a new electric drive system that Geely says achieved a comprehensive efficiency rating of 93.8%. That figure is not a universal measurement of an entire vehicle, and it was recorded under China's CLTC testing framework. Still, it is a remarkable headline number, especially because Geely says the system is designed for production vehicles rather than remaining a laboratory experiment. The company's 16-in-1 electric drive system is scheduled to appear in the Geely TT and combines multiple propulsion, charging, conversion, and control functions inside one integrated unit. To understand why that number attracted so much attention, we need to begin with what efficiency means in an electric vehicle and why it matters to drivers. Imagine filling a glass of water from a kitchen tap. If the glass has a tiny leak, you might not notice it immediately. A few drops escape, then a few more. But over several weeks, the amount of wasted water becomes significant. You are paying for water that never reaches the glass. An electric vehicle works in a similar way. The battery stores a fixed amount of energy, much like a tank stores fuel or a container holds water. When you press the accelerator, energy leaves the battery and travels through several systems before it reaches the wheels. It passes through the inverter, the motor, the reduction gear, the wiring, the cooling system, and various electronic controllers. Every stage creates some loss. Some of the energy becomes heat inside the motor. Some is lost through electrical resistance in cables and semiconductor components. Some disappears through friction in mechanical parts. Some is used by the vehicle's onboard electronics, pumps, fans, and cooling systems. By the time the energy reaches the wheels, not all of what you purchased at the charging station is still available to move the car. This invisible drain is called efficiency loss. It is one of the most important numbers in an electric vehicle, even though it rarely appears prominently in advertisements. Automakers focus on range, acceleration, battery size, and charging speed. But efficiency determines how effectively the vehicle uses every kilowatt hour stored in the battery. A more efficient car can travel farther with the same battery. It can use a smaller battery to achieve the same range. It can reduce charging costs and potentially lower the amount of raw material needed to build the vehicle. The difference between two systems may look small on paper. A drivetrain operating at 90% efficiency and one operating at 93.8% are separated by only a few percentage points, but those percentages apply every time the vehicle moves. Across thousands of kilometers, the energy difference becomes significant. That is why Geely's announcement attracted attention. According to the company, the Thunder electric drive system loses only 6.2% of the energy passing through it under the specified test conditions. If that result holds under broader and more demanding independent testing, it could mean that more of the battery's energy actually reaches the road. The company also connected the system to real-world demonstrations. A Geely TT sedan equipped with the drive system reportedly recorded energy consumption of 8.20 kilowatt-hours per 100 kilometers in a Qinghai Lake efficiency challenge, a result recognized by Guinness World Records. The vehicle also participated in a 46-kilometer continuous twin-car drift demonstration on wet asphalt. Those tests were designed to show two different things. The Qinghai Lake run focused on energy consumption. The drifting demonstration focused on thermal control and durability under extreme load. But before we examine those tests, we need to understand what is inside the silver box. The key idea is integration. For years, electric vehicles have used separate systems for propulsion, charging, power conversion, battery protection, thermal management, and low-voltage electronics. The motor sits in one housing. The inverter sits nearby. The onboard charger is installed elsewhere. A DC to DC converter supplies power to the vehicle's lights, displays, and control systems. The battery management system monitors the cells, while pumps, valves, and cooling circuits regulate temperature. Each separate unit requires its own casing, connectors, wiring, cooling paths, and control hardware. The result works, but it can be heavy and complicated. Every connector can corrode. Every cable adds weight. Every separate housing takes up space. Every additional component creates another possible failure point. Geely's answer was to combine these systems. Geely describes the Thunder system as a 16-in-1 intelligent electric drive. The number refers to the functions integrated into one assembly, including the electric motor, motor controller, reduction gear, DC to DC converter, onboard charger, battery management functions, thermal management systems, and software layers that coordinate their operation. The company says this integration removed more than 180 individual components and reduced high voltage wiring by approximately 30%, while also cutting low voltage wiring. Instead of scattering equipment across the vehicle, the engineers placed the core systems inside a single magnesium alloy housing. That approach has several potential advantages. The first is weight. A system with fewer separate housings, connectors, brackets, and cables can be lighter than a collection of independent modules. The company lists the total unit weight at roughly 75 kilograms, which is significant because weight directly affects range, acceleration, tire wear, and energy consumption. The second advantage is packaging. A compact integrated drive unit can be installed more easily in different vehicle platforms. Automakers may be able to use the same basic system in sedans, sport utility vehicles, vans, or other models with fewer modifications. The third advantage is reliability. Removing components can remove potential failure points. A connector that no longer exists cannot corrode. A separate fan that has been eliminated cannot seize. A cable that has been shortened has fewer opportunities to suffer damage. That does not mean integration automatically makes a vehicle more reliable. A single integrated unit can also be harder and more expensive to repair if something inside fails. Instead of replacing one small component, a technician may need to replace the entire module. The design must therefore balance compactness with serviceability. The fourth advantage involves thermal management. Electric motors, inverters, chargers, and power electronics all generate heat. If that heat is not removed efficiently, the system can lose performance or suffer long-term damage. Integrating the systems allows engineers to design shared cooling channels and control the temperature of the motor, inverter, and other components as one coordinated system. Geely says the Thunder system uses advanced cooling and control strategies to maintain efficiency under high loads. The company claims the all-wheel drive version can produce approximately 425 kilowatts, equivalent to roughly 570 horsepower, while operating on an 800-volt electrical architecture. Most older electric cars use 400-volt systems. An 800-volt platform can move the same amount of power with lower current, which can reduce some electrical losses and make high-speed charging more practical. The comparison is similar to widening a highway. If more lanes are available, more traffic can move through at the same time without creating the same level of congestion. The system is also designed for performance. Geely says the vehicle can accelerate from 0 to 100 kilometers per hour in approximately 3.8 seconds. That places it in a performance category traditionally associated with sports cars, even though the technology is being presented primarily as an efficiency and integration breakthrough. This is where the argument becomes more interesting. The Thunder system is not only about making an electric car faster. It attempts to make the entire propulsion architecture more compact, more efficient, and easier to scale across different vehicles. But high power and low weight create another challenge: heat. When an electric motor produces hundreds of kilowatts, large amounts of energy pass through the system in a short period. Even a highly efficient drivetrain produces some waste heat. At 93.8% efficiency, 6.2% of the input energy is still lost under the relevant test conditions. At high output, that remaining percentage can represent a substantial thermal load. A system that cannot remove that heat will eventually reduce its power or shut down to protect itself. That is why thermal control is just as important as the efficiency number. Geely attempted to demonstrate this during a demanding test at Qinghai Lake. The lake sits more than 3,000 meters above sea level, where the air is thinner and temperatures can change quickly. High-altitude roads, strong wind, and rough surfaces create additional stress for a vehicle. The company brought a Galaxy TT sedan to the area and worked with Guinness World Records officials to measure the vehicle's energy use. According to the reported result, the car consumed only 8.20 kilowatt hours per 100 kilometers during its route around the lake. That figure is extremely low compared with the energy consumption of many larger electric vehicles. But energy consumption depends on many factors, including vehicle size, speed, tires, weather, route elevation, driving style, and testing methodology. A single record run cannot automatically represent what every owner will experience in daily traffic. The test is still useful because it shows what the complete vehicle can achieve under a defined set of conditions. It demonstrates that the drivetrain, battery, software, tires, and aerodynamics can work together efficiently. Then, Geely attempted a very different demonstration. Instead of driving gently for maximum efficiency, the company placed two Galaxy TT sedans on a wet asphalt track and instructed the drivers to drift continuously. The vehicles traveled side by side for 46 kilometers, with the tires spinning and the electric motors operating under intense load. Drifting is one of the harshest demonstrations for an electric drivetrain. The tires constantly lose traction, which forces the motors to work aggressively. The power electronics must respond quickly, while the cooling system must remove heat continuously. Under ordinary driving, the vehicle alternates between acceleration, cruising, braking, and periods of low demand. During a prolonged drift, the motors can remain under heavy stress for much longer. If the cooling system cannot keep up, temperatures rise, and the vehicle will eventually reduce power or shut down. Geely reported that the two vehicles completed the 46-kilometer drift without overheating or losing performance. The demonstration was recognized by Guinness World Records as the longest continuous twin-vehicle electric drift. This does not prove that the car is more efficient during ordinary commuting. It tests a different quality, the ability to manage high heat and sustained power. The Qinghai Lake run was about energy consumption. The drifting test was about endurance and thermal control. Together, the two demonstrations were designed to show that the integrated drivetrain could be both economical and powerful. That combination is difficult to achieve. In many vehicles, efficiency improves when the system operates gently, while performance demands create higher losses and more heat. An advanced drivetrain must therefore remain efficient across a wide range of operating conditions. The Thunder System's integration may help because the motor, controller, cooling system, and software can exchange information quickly. If the temperature rises in one area, the control system can adjust power delivery or cooling behavior immediately. Separate components connected through longer wiring paths may not respond as efficiently. The system also uses software as part of its architecture. Intelligent control layers can determine how much power should come from the front motor, how much should come from the rear motor, when to reduce output, and how to balance performance with energy use. Software can also manage regenerative braking. When the driver slows down, the electric motor can act as a generator and send some energy back to the battery. The amount of recovered energy depends on vehicle speed, battery temperature, battery charge level, tire grip, and the driver's braking request. If the systems are integrated closely, the vehicle can coordinate regenerative braking, battery protection, motor temperature, and stability control more effectively. However, it is important not to treat 93.8% as a permanent universal value. The number is associated with a particular measurement framework. Chinese automakers commonly use the CLTC cycle, which is known to produce more optimistic range and efficiency results than some real-world driving conditions and international testing cycles such as EPA or WLTP. A vehicle's performance can vary substantially between laboratory cycles and actual use. Highway driving, winter temperatures, strong air conditioning, heavy cargo, hills, traffic, and high-speed acceleration all affect energy consumption. That is why independent testing matters. The 93.8% claim is significant as a manufacturer-reported benchmark, but the automotive industry will want to see how the system performs under standardized testing outside the company's own facilities. This is where skepticism enters the story. Some engineers have pointed out that the 93.8% figure may refer to the system's comprehensive efficiency under the CLTC framework rather than the efficiency of every part of the drivetrain under every possible condition. That distinction is important. A motor may achieve its highest efficiency at a particular speed and load, while real driving requires it to operate across a wide range. An electric drive system is not judged only by its peak number. Engineers also examine partial load efficiency, high temperature performance, durability, noise, vibration, repair costs, manufacturing consistency, and behavior after years of use. The same caution applies to the Qinghai Lake record. Guinness certification confirms that a particular vehicle achieved a particular result under a defined test. It does not mean every vehicle with the same drivetrain will automatically consume 8.20 kilowatt-hours per 100 kilometers in every country. Still, skepticism does not erase the engineering achievement. A compact 16-in-1 system weighing around 75 kilograms, producing hundreds of kilowatts, operating on an 800-volt architecture, and supporting record-setting demonstrations represents a serious design effort. The bigger question is whether the architecture can be manufactured reliably and installed across many vehicle models. If it can, the effect could extend beyond one Geely sedan. Integrated electric drive systems can reduce assembly complexity, simplify vehicle platforms, and potentially lower the cost of producing electric cars. That brings us to the competitive implications. Traditional automakers built their businesses around mechanical complexity. Internal combustion vehicles contain engines, transmissions, exhaust systems, fuel systems, cooling circuits, and hundreds of moving parts. Electric vehicles remove many of those components, but the electric drivetrain still contains several separate electronic and mechanical systems. A company that integrates those systems more effectively may reduce cost and manufacturing time. It may also create a platform that can be adapted to different vehicle sizes with fewer engineering changes. This is where Chinese automakers have been moving quickly. Companies such as Geely, BYD, NIO, XPeng, and others have invested in motors, power electronics, battery systems, software, semiconductors, and vehicle platforms simultaneously. Their goal is not merely to assemble electric cars. It is to control more of the technology inside them. Geely's Thunder system fits into that broader strategy. The company controls a wide range of automotive brands and has experience producing vehicles for different markets. An integrated electric drive could potentially be shared across several products, spreading development costs over larger production volumes. The impact on vehicle design could be substantial. A lighter drive unit gives engineers more flexibility in how they distribute weight. A smaller package can create more room for passengers or batteries. Fewer cables can simplify assembly. Shared components can reduce the number of unique parts required across a vehicle lineup. Lower part counts can also improve supply chain efficiency. If one integrated unit replaces several separate suppliers and modules, the automaker may need fewer logistics routes and fewer assembly operations. But this also concentrates risk. If the integrated unit has a major defect, a larger number of vehicles could be affected. The system's repairability will become especially important. Consumers may like the simplicity of fewer visible components, but they will also want affordable maintenance. If a failure requires replacing a large integrated box instead of one small module, repair costs could increase after the warranty expires. This is one reason why mass market success cannot be measured only by efficiency. The drivetrain must survive high mileage, extreme temperatures, potholes, water exposure, accidents, and years of charging cycles. It must also be serviceable in markets where trained technicians and replacement parts may be limited. The global market will provide that test. Chinese electric vehicles are already expanding into Europe, Latin America, Africa, Southeast Asia, and the Middle East. In countries with limited local manufacturing, buyers often care about price, range, reliability, and access to service more than the nationality of the brand. A more efficient drivetrain could make Chinese electric vehicles attractive to commercial fleets. Delivery vans, taxis, buses, and ride-hailing vehicles travel far more kilometers per year than private cars. A small improvement in energy consumption can become a significant financial saving when multiplied across a large fleet. For a fleet manager, the calculation is straightforward. The vehicle must be affordable to buy, cheap to charge, reliable in daily operation, and easy to repair. A lighter and more efficient drivetrain could reduce energy use while also lowering the battery capacity required for a given route. That could create a competitive advantage in regions where electricity is expensive or charging infrastructure is limited. But the same international expansion also creates political resistance. Governments in Europe and North America are concerned about subsidies, supply chain dependence, data security, and the effect of Chinese imports on domestic manufacturers. Tariffs and local content rules can slow the spread of Chinese electric vehicles. Even so, markets without strong tariff barriers may become important testing grounds. Fleet operators in Africa, Latin America, and Southeast Asia can compare Chinese vehicles with more expensive alternatives based on their real operating costs. If the drivetrain performs well in hot climates, heavy traffic, poor road conditions, and long working hours, the technology could gain credibility quickly. If the real-world efficiency falls far below the headline number, buyers will notice just as quickly. This is why the current industry reaction is more complicated than simple panic. The 93.8% figure is impressive, but rival automakers will not redesign their product lines based on one announcement. They will disassemble the system, test it, examine its manufacturing methods, and compare it with their own designs. They will ask how much of the efficiency comes from the motor, how much comes from the inverter, how much comes from thermal management, and how much is attributable to the test cycle. They will examine the durability of the magnesium housing, the cooling channels, the semiconductor materials, and the software controls. They will also ask whether the system can be produced at scale without increasing warranty risk. The most meaningful part of the announcement may not be the exact percentage. It may be the decision to integrate so many functions into one production-oriented unit. The global auto industry has been moving toward integration for years, but companies have often balanced integration against modularity. A highly integrated unit can be lighter and more efficient, while a modular system can be easier to repair and adapt. Geely is making a strong argument for integration. The next few years will reveal whether that argument works beyond controlled demonstrations. The technology also raises a larger question about how electric vehicles should be judged. Most buyers focus on battery capacity and official driving range. A larger battery usually produces a longer range, but it also adds weight and cost. If the drivetrain becomes more efficient, the automaker can achieve the same range with fewer battery cells. That could reduce the demand for lithium, nickel, cobalt, copper, and other materials. It could also lower the energy required to manufacture the battery itself. A smaller battery pack may charge faster, weigh less, and place less stress on the chassis and suspension. Efficiency improvements are therefore not just about saving electricity after the car leaves the factory. They can influence the entire life cycle of the vehicle. A lighter car consumes less energy, which allows for a smaller battery. A smaller battery reduces weight, which lowers energy consumption again. The effect can reinforce itself, but this logic has limits. If automakers use efficiency gains to add more performance, larger wheels, heavier interiors, or bigger displays, some of the benefit may disappear. A more efficient drivetrain does not automatically produce a more efficient vehicle if the rest of the design becomes heavier. That is why the most important application may be in commercial vehicles. Delivery vans, taxis, buses, and urban transport systems can use efficiency gains directly because they operate on predictable routes and accumulate high annual mileage. A fleet vehicle that saves a small amount of electricity on every trip can produce meaningful savings over several years. If the drivetrain also reduces maintenance requirements, the total operating cost can fall further. The integrated design may also help with vehicle production. A single drive unit can be installed as a complete module, rather than requiring several separate systems to be assembled and connected independently. That may reduce factory labor, shorten production time, and make it easier for automakers to establish assembly operations in new markets. However, the same modularity can create a risk of dependence. If one supplier controls the integrated system, the automaker may have less flexibility to change individual components. A problem in the drive unit could affect multiple vehicle models at once. Supply chain resilience will therefore matter. The company must be able to produce motors, inverters, chargers, controllers, sensors, and cooling components in sufficient quantities. It must also maintain software support for years after the vehicle is sold. The software component is becoming increasingly important. Modern electric drivetrains are controlled by algorithms that manage torque, braking, temperature, battery state, traction, and efficiency. Over-the-air updates can improve performance, but they also create cybersecurity and long-term support requirements. An integrated electric drive system may become more like a computer than a traditional engine. It will require software updates, diagnostics, secure communication, and protection against unauthorized access. That creates a new competitive battlefield. Automakers are no longer competing only on horsepower or battery range. They are competing on power electronics, operating systems, data, thermal control, and the ability to improve a vehicle after it has been sold. Chinese manufacturers have invested heavily in those areas, often working with domestic suppliers and semiconductor companies. This can shorten development cycles and allow rapid experimentation across multiple vehicle models. Western automakers are also investing in similar systems, but many face legacy challenges. Their existing factories, supplier networks, dealer arrangements, and engineering organizations were built around internal combustion vehicles. Changing the architecture of the car requires changing the organization around it. That is difficult even for companies with enormous resources. It is also why a single integrated unit can be strategically important. It represents a shift from improving individual components to redesigning the relationship between them. The efficiency number is the visible headline. The deeper change is architectural. Instead of asking how to make the motor slightly better, engineers ask how to remove unnecessary connections between the motor, inverter, charger, battery, and cooling system. Instead of adding another component to solve a problem, they try to eliminate the problem through integration. This approach can produce dramatic improvements when executed correctly. But it also makes validation more important. A complex system hidden inside one box must be tested under every condition, because consumers cannot easily inspect or repair the individual functions inside it. The test of credibility will therefore happen in independent laboratories, on public roads, and inside commercial fleets. The key questions are simple. Does the 93.8% figure remain competitive under EPA or WLTP testing? How does the system perform at highway speeds? What happens in cold weather? How much power does it use while climbing? How does the battery behave after 200,000 kilometers? What does it cost to replace the unit outside warranty? Until those questions are answered, the Thunder system should be seen as a promising engineering development rather than a proven industry revolution. But even the questions themselves show how far the conversation has moved. A few years ago, many global automakers were still debating the pace of electric vehicle adoption. Now they are being forced to examine the architecture of electric propulsion itself. The most honest conclusion is that Geely's 93.8% figure is both impressive and incomplete. It is impressive because it reflects a serious attempt to combine multiple electric vehicle functions into one compact, high-power, 800-volt system. The reported 16-in-1 architecture weighs approximately 75 kilograms, eliminates many separate components, reduces wiring, and has supported energy efficiency and thermal endurance demonstrations. Geely has positioned the technology as a production system rather than a purely experimental design. It is incomplete because a single headline number cannot describe the performance of an entire vehicle under every possible condition. Efficiency depends on the test cycle, speed, temperature, load, road surface, battery state, and driving style. The 93.8% result was reported under China's CLTC framework. That makes it useful as a domestic benchmark, but international comparisons require testing under equivalent conditions. A system that achieves a remarkable result in a controlled cycle still has to prove how it performs in real traffic, during long highway drives, in winter weather, on steep roads, and after years of use. The Qinghai Lake efficiency record provides additional evidence that the vehicle can operate with very low energy consumption under specific conditions. The 46-kilometer drift demonstration provides evidence that the cooling system can handle sustained high loads. Neither test answers every question, but together they show that the engineering is not merely a claim on a presentation slide. The global auto industry is unlikely to remain silent forever. Rival companies will study the design, test the components, and develop competing systems. Some may copy the integrated architecture. Others may argue that their modular systems are easier to maintain or adapt. The result could be a new phase of competition in which the most important improvements happen inside the drivetrain rather than on the exterior of the car. For consumers, that competition could produce lighter vehicles, smaller batteries, faster charging, lower energy bills, and improved performance. For fleet operators, it could reduce the cost of every kilometer driven. For automakers, it could lower manufacturing complexity while creating new challenges around repairability and software support. The consequences could also reach markets that are not traditionally seen as centers of automotive innovation. A highly efficient drivetrain does not require the same charging network as a large battery if the vehicle uses less energy for each kilometer. In regions where electricity is expensive or charging stations are limited, efficiency can matter as much as battery capacity. That may give Chinese electric vehicles an advantage in Africa, Latin America, Southeast Asia, and other growing markets. The vehicles may not need to win every technology category. They only need to offer a combination of price, range, reliability, and operating cost that local buyers find convincing. The next 3 years will be important. Independent testing will reveal whether the efficiency figure translates into broader conditions. Fleet operators will determine whether the vehicles remain reliable under daily commercial use. Repair networks will reveal whether the integrated design is affordable to maintain. Regulators will assess whether the vehicles meet safety and environmental standards in different markets. If the system performs as claimed, Geely will have accomplished more than producing an efficient motor. It will have demonstrated that a highly integrated electric drive architecture can move from the laboratory into production and compete globally. If the real-world results fall substantially below the headline, the technology may still be valuable. Even a smaller improvement could reduce vehicle weight, battery size, wiring, and manufacturing complexity. Engineering breakthroughs do not have to meet their most dramatic claims to influence the market. The silver box, therefore, represents a possibility rather than a final verdict. It may become the foundation for a new generation of electric vehicles. It may inspire rival automakers to integrate their own systems more aggressively. Or it may be remembered as an ambitious demonstration whose real-world results were more modest than the launch presentation suggested. Either way, the direction of the industry is clear. Electric vehicles are moving away from collections of separate components and toward tightly integrated systems in which motors, inverters, chargers, batteries, cooling circuits, and software work as one machine. That is the real story behind the 93.8% number. The question is no longer whether electric vehicles can become more efficient. The question is how much efficiency can be gained by redesigning the entire powertrain from the beginning. For years, global automakers competed over battery capacity, horsepower, screen size, and acceleration. Now they are being pushed to compete over the invisible systems that determine how much energy actually reaches the road. The silver box on the stage looked ordinary because the most important automotive breakthroughs often do. The engineering is hidden inside the casing, buried beneath the floor, and controlled by software most drivers will never see. But if Geely's claims hold up under independent scrutiny, that unremarkable box could influence how electric cars are built across multiple continents. Not because it has created energy from nothing, and not because one test figure permanently settles the efficiency race, but because it demonstrates the power of removing complexity rather than continuously adding to it. A lighter, more integrated, more efficient drivetrain could allow future vehicles to use smaller batteries, travel farther, charge faster, and cost less to operate. And that is why the world's automakers are paying attention. The future of the automobile may not be decided by the largest battery or the most dramatic design. It may be decided by the machine hidden inside a simple silver box.